Hello, and welcome to this lesson on plotting, interpreting, and using graphs showing the quantity of product formed or reactant used up against time in a chemical reaction. In today's lesson, we will learn how to plot graphs displaying the quantity of product formed or reactant used up over time. Then, we will understand how to interpret these graphs to determine the rate of a chemical reaction. So far, you've started exploring rate calculations, and you are familiar with measuring quantities involved in reactions. Building on this foundation, today's lesson will deepen our understanding by showing how we can visually represent and analyze the progress of a reaction. This visual and analytical approach will advance our chemical understanding even further. Let's get started. First, we'll start with plotting the graph. Imagine you have conducted an experiment where you've measured either the amount of reactant used up or the amount of product formed at different time intervals during a reaction. You now want to represent this data visually on a graph. On the x-axis, you will plot time, usually in seconds or minutes. On the y-axis, you will plot the quantity of product formed or reactant used up, often in moles, grams, cubic decimeters, or cubic centimeters. Once you have your data points from the experiment, you will plot each point on the graph and then join these points to form a curve. The shape of this curve tells us about the progress of the reaction. For example, suppose you carried out a reaction between magnesium and hydrochloric acid, where magnesium reacts to form magnesium chloride and hydrogen gas. You measured the volume of hydrogen gas produced every 10 seconds using a gas syringe. On the x-axis, you would plot time in seconds. On the y-axis, you would plot the volume of hydrogen gas produced in cubic centimeters. As time progresses, you will see the volume of hydrogen gas increase as the reaction proceeds. Eventually, the curve will level off, indicating that the reaction is slowing down or has stopped, as no more hydrogen is being produced. This graph allows you to visually interpret how the reaction rate changes over time and when the reaction reaches completion. At the beginning of the reaction, the curve is steep because the rate of reaction is fastest. This is due to the high concentration of reactant particles, which means that there are plenty of particles available to collide with each other. More frequent collisions lead to a higher chance of successful reactions, causing the reaction to proceed quickly. As the reaction progresses, the curve begins to level off. This indicates that the reaction is slowing down. Over time, the reactant particles are being used up, so there are fewer particles left to collide. This results in fewer successful collisions, therefore the reaction slows down. Eventually, the curve becomes flat when the reaction has finished. At this point, one or more of the reactants have been completely used up, and no further collisions can occur, meaning that no more product is being formed and the reaction has stopped. By observing the shape of the curve, you can gather insights into the kinetics of the reaction. To determine the rate of reaction at a specific point in time, you can draw a tangent to the curve at that point. A tangent is a straight line that just touches the curve at a particular point and represents the slope at that point. The slope of the tangent indicates the instantaneous rate of reaction. To calculate the gradient of this tangent, you need 2 points on this line. The gradient is given by the change in the y value, quantity of product formed or reactant used up, divided by the change in the x value, time. Mathematically, this is often expressed as the change in y divided by the change in x. The steeper the tangent, the faster the rate of reaction at that moment. Finally, these graphs are not just for analysis. They are also powerful predictive tools. By understanding the shape and behavior of the curve, you can estimate how much product will be formed or how much reactant will be used up by a certain time. You can also compare similar graphs for different reactions to determine which reaction is faster or slower. Finally, you can even infer the effects of changing conditions, such as temperature or concentration, on the rate of reaction by comparing the changes in the curves under different conditions. Let's dive into some GCSE level questions to apply our understanding of plotting, interpreting, and using graphs showing the quantity of product formed or reactant used up against time in a chemical reaction. Question 1. You conducted an experiment where you measured the amount of gas produced in a reaction every 10 seconds. Your data is as follows. At 0 seconds, the volume of gas is 0, then subsequently 12, 22, 29, 34, 36 centimeters cubed every following 10 seconds. Plot this data on a graph. Firstly, draw the x-axis for time, in seconds, and the y-axis for the volume of gas, in cubic centimeters. Then mark your axes with appropriate scales. For example, the x-axis could be marked in 10-second intervals, and the y-axis could be marked in 5 cubic centimeter intervals. Next, plot your data points. Finally, join the points to form a curve. Question 2. Using the graph from example 1, describe the rate of reaction over time. At the start of the reaction, 0, 10 seconds, the curve is steep, indicating a high rate of gas production. Between 10 and 30 seconds, the curve starts to become less steep, showing the rate of reaction is slowing down. From 30 seconds onward, the curve levels off, suggesting the reaction rate has significantly decreased and is approaching completion. From this interpretation, we can see that the reaction rate is highest at the beginning and decreases over time. Let's look at one more question. Determine the rate of reaction at 20 seconds using the graph you plotted in example 1. Firstly, draw a tangent to the curve at the 20-second mark. Then, select 2 points on this tangent line. Here, the tangent line passes through the points 15, 17 and 25, 27. These points can be used to calculate the gradient. Finally, calculate the gradient, rate of reaction, using the formula. Change in y over change in x. The change in x is 25 seconds minus 15 seconds, giving us 10 seconds. The change in y is 27 cubic centimeters minus 17 cubic centimeters, giving us 10 cubic centimeters. Therefore, the rate of reaction is 10 cubic centimeters over 10 seconds, equaling 1 cubic centimeter per second. This means that at 20 seconds, the rate of gas production is 1 cubic centimeter per second. In today's lesson, we focused on plotting, interpreting, and using graphs that show the quantity of product formed or reactant used up against time in a chemical reaction. We started by learning how to plot these graphs, with time on the x-axis and the quantity of product or reactant on the y-axis. We then discussed how to interpret the shape of the curve, noting that a steep curve indicates a fast reaction rate at the beginning, which then slows down and eventually levels off as the reaction completes. Next, we explored how to determine the reaction rate at specific points using tangents, where the slope of the tangent represents the instantaneous rate of reaction. By understanding reaction rate curves, we gain valuable insights into how reactions progress over time, allowing us to predict and control the speed of reactions in practical and industrial applications, ultimately enhancing our ability to optimize chemical processes. Watch the rest of the GCSE Chemistry course at SoftFOS Education.